Hello and welcome to this video lesson on metal aqua ions. Specification reference 3.2.6. And in today's video lesson what we want to do is the following three or four things. The first one being what happens when metal compounds dissolve in water. Well, as you might have guessed from the title, we get these things called metal aqua ions. The aqua being the connection to water. And you get some interaction between water molecules and the metal ions from the metal compound. And we're going to have a look at that in some detail. And also, we want to answer this question here. How come metal aqua complexes are acidic? Some of them are acidic, and we want to understand that process of how they are becoming acidic. Some of them are actually amphoteric as well, so we'll understand that as well. And then we want to understand the different ways of hydrolyzing metal aqua ions. And this word hydrolyzing, let's just highlight that. Hydrolyzing, it's not the same as hydrating. So hydrating is adding water molecules, and hydrolyzing is actually breaking water molecules. And so what are the different ways of hydrolyzing metal aqua ions? And what's the point of it anyway? Why are we studying it? We'll look at that as well. So that's what we're going to do. We're going to start off with the first one. What happens when metal compounds dissolve in water? So the first thing to point out here is what metal compounds are we interested in? Well, your spec requires you to know about 4 different metal ions. So we've got 2 times 2 plus ions, and they are an Fe2 plus ion and a copper 2 plus ion. The anions are not important. So these are the metal ions from the metal compounds, and that's what we're interested in. And we also need to know about 2 3 plus ions as well. And the 3 plus ions that we're interested in is Fe 3 plus and aluminium 3 plus. Aluminium not being a transition metal, but nevertheless included in this topic. So they are the 4 metal ions that we're most interested in. And the first thing we're going to do is look at the complexes formed when these 4 dissolve in water. And the short answer to the question is that the metal ions get hydrated. Hydrated means adding water molecules to them. And they, when I say water molecules are added to the ions, we mean they form coordinate bonds. Which you'll remember are bonds whereby one of the lone pairs are provided by one of the molecules, in this case water. So the lone pair provides both of the bonding electrons to make a coordinate bond between the water molecule and the metal ion. And in these 4 cases we get 6 water molecules. Acting as ligands, each attached to the metal ion by a coordinate bond in an octahedral shape. So what we're going to do now is draw a couple of them. Let's draw a 2 plus and a 3 plus complex. So let's start off with copper 2 plus. So let's say we have a copper 2 plus ion that goes in the middle, and then we're going to have 6 water molecules. So let's draw our water molecules like this. We're going to have one of them here with its lone pair. I'm going to draw the water molecule like this, and that's the lone pair that forms the coordinate bond, and the coordinate bond is going into the page. Right, so we're going to draw it as a wedge, and we've got another water molecule that makes its coordinate bond also into the page towards the copper ion, and draw its lone pair that's providing the bonding electrons, and the water molecule that we'll draw like that. And so we've also got another pair of water molecules at the back who are going to provide their coordinate bond from behind the screen into the copper atom. So we draw that as a dotted line, and there's going to be two of those, so I'll draw two dotted lines while I've got my green pen out, and we will draw our water molecules like so. Don't forget the lone pairs. So that's 4 of our 6 water molecules accounted for. The other 2 are from above and from below in the plane of the screen. So we draw those as just normal solid arrows. And again, we'll do our lone pair, our oxygen, and our hydrogens. Our lone pair, our oxygen, and our hydrogens there of our water molecules. And you can see this octahedral shape. Let's just put some dotted lines here. So we've got this sort of square shape with our 4 electrons, the 2 at the back and 2 at the front, and then our two other water ligands above and below. And so that's what our copper complex looks like. It's called a hexa aqua copper complex. Let me write that down. Hexa for 6, aqua because the ligand is water, copper because our metal ion is copper, and it's a complex, so we call it hexa aqua copper complex. Now, didn't we mention that the copper had a 2+ charge? We mustn't forget about that, but as usual we draw that in our square brackets like so, and so that's what the complete hexa aqua copper complex looks like. Now, for the sake of completion, it looks very. We're going to do a aluminium hexa aqua aluminium complex. So we've done this one here. The iron is just the same, so we won't bother drawing that out. And in fact, the aluminium is just the same with a tiny difference, but nevertheless, we'll draw it out for completeness. So again, we've got an aluminium 3+ ion in the middle, and in the same way as before, we're going to have 6 water molecules. So we're going to draw our square in the plane perpendicular to the screen. So these 2 water molecules are going to, the first 2 are going to go into the screen. These 2 are going to come from behind the screen. So we draw them like dotted and wedges like that. And so we'll draw our lone pairs and our oxygen and our 2 hydrogens. Lone pairs, oxygen, 2 hydrogens, lone pairs, oxygen, 2 hydrogens, lone pairs, oxygen, 2 hydrogens, like that. So that's our square shape that's perpendicular to the screen. And then of course we need 2 more, also making coordinate bonds. One from above, one from below. So in the same way we'll do our water ligands like that. And now the aluminium ion is a 3+ ion. That's just to illustrate the square. Our aluminium ion is a 3+ ion, and our water molecules are neutral, so they don't change the charge. So the whole complex retains the charge that the aluminium ion has, and so that of course is 3+. So in the same way, we're going to draw our square brackets with a 3+ there, and that is now called a hexa aqua aluminium complex, like that. And in shorthand, we draw the formulas of the two like this. Going back to the copper one, we would have copper, and in brackets we put our 6 water ligands, and in square brackets we put our charge like that. And on the right hand side, our aluminium one would be in the same way. We've got aluminium, we've got 6 water ligands, and the whole thing has a 3+ charge. So that's how we write them in shorthand form as the formulas. And that's what happens when metal compounds, particularly these metal compounds, these 4 metal ions, when they dissolve in water, they make complexes with 6 water ligands, each attached to the metal ion by a coordinate bond in an octahedral shape. And there you have the answer to the question. So moving on to our second question, and that was how come metal aqua complexes are acidic? That's what we're going to do now. First, let's just get our heads around this question. Let's remind ourselves what we mean by acidic. So for it to be acidic, we need to have something release hydrogen ions or protons. Something must donate protons or hydrogen ions to make it acidic. And while we're at it, why don't we just remind ourselves of the definition of hydrolysis. So hydrolysis in this case is acid hydrolysis. Hydrolysis is a reaction with water molecule where some bond gets broken, and in this case it's another water molecule that's get broken, where a water molecule dissociates because a bond gets broken. So that's hydrolysis, and we're not talking about hydration. And so the reaction that we're about to study is a hydrolysis reaction. So let's write out. Well, let's start off with first of all, let's start off with our metal 2+ ions. Okay, so and we're going to use the iron as the example. We're going to switch from copper 2+ to iron 2+. They both react similarly, but let's switch to iron. So our iron aqua complex is written like this. We've got an iron 2+ ion with 6 water ligands, and as I said, it was a 2+ ion, so the whole complex has a 2+ charge because the water molecules are neutral. Let's be complete, putting in our aqueous state symbol. And then we say this hydrolysis reaction is a reaction with water, so we're going to add some water to it. And then we also say the hydrolysis reaction requires something to get broken. Well, what gets broken is one of these water ligands. And so I'm going to draw the equilibrium sign there because it's not a complete reaction. So one of those water ligands gets broken and a hydrogen ion gets released. So that we would draw like this. So we've still got the iron 2+ ion in the complex, but if we've released a proton from a water molecule, what is left is just a hydroxide ion, and so that is one of the ligands. Now instead of the water molecule, it's a hydroxide ion, and we still have the other 5 water ligands still attached to the complex, and we write in our square brackets. But this is no longer 2+, right, because we've lost a hydrogen ion, which has a 1+ charge. So what's left is only 1+. And that hydrogen ion has reacted with this water molecule to make a hydroxonium ion, H3O+. And that is what makes it acidic. All right, so just to recap, what we've done here is we've done a hydrolysis reaction, which is a reaction with a water molecule that involves another molecule, in this case also a water molecule, breaking down. So one of our water ligands, one of our 6 water ligands, has lost a hydrogen ion, and what remains is a hydroxide ion. That's it here. It remains as a ligand in the same complex, but it's released its proton, and that proton reacts with an adjacent water molecule, not one of the ligands, but a wandering water molecule, and makes a hydroxonium ion, which is this H3O+ here. And hence, this hydrolysis reaction has resulted in an acidic solution. Now, this dissociation doesn't happen to many of the molecules, and so it's weakly acidic. So we'll write that down. I'll just put weak here, all right, because not many of the water molecules dissociate like that. So what we're going to do now is we're going to do the metal 3+ ion example, and it's going to look nearly exactly the same, but it allows us to make a differentiation slightly later on. So the 3+ ion that we can use is our aluminium ion. So it's an aluminium 3+ ion, and it starts off being surrounded by 6 water ligands like before, but it's a 3+ ion, so the complex has a 3+ charge, and in the same way that complex is going to react with a adjacent water molecule, and it's going to react in the same way. One of those water ligands is going to break down, and so our aluminium ion is going to be surrounded by 5 water ligands, right? But one of those water ligands, the 6th one, has turned into a hydroxide ligand because the water molecule has lost one of its hydrogen ions to leave a hydroxide ion like that. So in the same way as we lost a positive charge, our 3+ charge on the left turns into a 2+ charge on the right, because our hydrogen ion has left its electron there and has gone with its proton and jumped onto a water molecule to make this hydroxonium ion just as before, which is also acidic. But the interesting thing is it's less weak, right? It's not strong, right? But it's less weak than our metal 2+ complex. So that begs the question, why is our metal 3+ complex more acidic than our metal 2+ ion? And it's down to the charge density of the 3+ ion. So the aluminium ion and the Fe3+ ion have, as the name suggests, 3 positive charges, whereas our copper and our iron have only 2 positive charges. So our charge density, so our M3+ ions, they have a much higher charge density. I mean, the copper and the iron 2+ and the iron 3+ are all about the same size, but the aluminium is even smaller, so the smaller size of the aluminium plus its extra positive charge means that that charge is concentrated in the same or smaller volume, so making the charge density much higher for our M3+. So that higher charge density leads to greater polarization of the oxygen-hydrogen bonds. So let's write that down. So greater polarization of the OH bond in the water. So I'll draw that to make it extra clear. So if we've got an M3+ ion, and then let's do it in black. Right, so we're going to have a coordinate bond, and we're going to have an oxygen atom in our water molecule. We've got our two hydrogen atoms here. So what we're saying is that the electrons in this bond here are more attracted in this direction towards the oxygen, because our 3+ charge has attracted these electrons more towards the metal ion. So everything, all the electrons get dragged towards the metal 3+ ion, and in which case our oxygen-hydrogen bond, this one here, gets weak and breaks. And those two electrons that were in that bond, they go with the oxygen, leaving the hydrogen as not an atom but an ion, like that. And so that's how it works. So we've got a higher charge density leading to a greater polarization of the bond, and that weakens the bond, so more hydrogen ions are released. So that is the why. So just to summarize that slide, what we've done is we've described the hydrolysis reaction that leads to acidic solutions when these metal ions dissolve in water, and we've stated that the 3+ ions are more acidic than the 2+ ion complexes, and then we've explained why, and that's because the metal 3+ ions, the Fe3+ and the Al3+, have higher charge density, and that draws the electrons in the oxygen-hydrogen bond towards the oxygen and towards the metal. That weakens that oxygen-hydrogen bond, and so more of the hydrogen ions are released because of more dissociation of that bond. So there we have it. Okay, we move on now to this question here. What are the different ways of hydrolyzing metal aqua ions, and what's the point of doing so? Okay, before we delve into it, let's make sure that we understand what we're trying to set out to do. First of all, why don't we remind ourselves what hydrolyzing means? So in this case, so if we represent the metal ion with M, and we're going to have 6 water ligands in a complex, let's say it was an M2+ ion. If we hydrolyze that, then what we're doing is we're exchanging one of the water ligands for a hydroxide ligand. So that's what we mean by hydrolyzing again. Now the different ways, there are 3 different ways that we can facilitate this. In addition to the bit of hydrolyzing that goes on just when the metal compound dissolves, a little bit of hydrolysis happens when it dissolves anyway, but these are 3 supplementary ways of more hydrolyzation of metal aqua ions, and the first way we're going to look at is by just adding hydroxide ions. And the second way is we're going to add ammonia. And the third way is we're going to add sodium carbonate. So there are three different ways of hydrolyzing metal aqua ions. Let's remind ourselves first what metals. So we've got Cu2+, we've got Fe2+, and we've also got two 3+ ions. We've got Fe3+, and we've got aluminium 3+. There are four metal aqua complexes that we're interested in. So that's unpicked the first question, and the second question, what's the point of all this? Well, the point of it is for identification. If we wanted to identify which one of these four ions we've got, then we might do one or more, all of these hydrolysis reactions, adding hydroxide, adding ammonia, adding sodium carbonate, and we would get different products produced, and whatever products were produced would tell us what ion we started off with, so we could identify the metal ions. So that's the point. So let's delve into a bit more detail now. And let's start off with number one. We're going to add hydroxide ions. And let's first of all do it to a metal 3+ ion, so either the Fe3+ or the aluminium 3+. So we're going to start off with that. Just when we dissolve a metal 3+ ion in water, we get a little bit of hydrolysis, and we're going to start off by writing that reaction down again. So we've got our metal ion, we've got our 6 water ligands, and it's a 3+ ion, so our complex still has 3 pluses to it. And as before, when it dissolves, we get that complex and it reacts with water, all right, and a little tiny bit of hydrolysis, acidic trihydrolysis happens, such that one of the water ligands is broken down into a spare hydrogen ion and this hydroxide ion, and we're left with 5 water ligands still there, and we've lost one of our positive charges, and we've made a hydroxonium ion because our hydrogen ion from the water ligand has added on to the water molecule that is here. Okay, so that's what we've got when we just dissolve it in water. But let's say we add some hydroxide. If we add some OH minus, then the hydroxide is going to react with the hydroxonium ion, and that's going to make 2 water molecules, and that's therefore going to suck this hydroxonium ion out of solution, which is going to encourage more of the forward reaction in this equilibrium reaction, a la Le Chatelier. So in that case, what we're going to get is we're going to get a further hydrolysis of this complex here. So I'm just going to draw a dotted line over like this, and we're going to start again with that product. So we've got a metal ion, it's the metal 3+ ion, we've got 1 hydroxide ligand and 5 water ligands, all on with a 2+ charge, and it is also reacting with a water molecule, and the same thing is going to happen. We're going to get one of these 5 water ligands being hydrolyzed into hydroxide, such that we now have 2 hydroxide ligands and only 4 water ligands. And in the same way as before, we've lost one of our positive charges, so that's only 1 plus now, and that's created another hydroxonium ion, which then is soaked up by the hydroxide ions that we've added to make another 2 water molecules. So the same thing can happen again. We get this product here turning into a reactant and reacting with another water molecule in the same way. So let's complete the step. So we've got our 2 hydroxide ligands, our 4 water ligands with 1 plus charge, reacting with another water molecule. In the same way as before, because we've sucked out that product, so we've moved that equilibrium to the right, and in this case we've got 3 hydroxides and 3 waters, because the metal ion can only fit 6 of these ligands around it. But now it has no charge, so we don't bother drawing the square brackets, and instead we just give it its state symbol here, which is a solid, because it has no charge, it's insoluble, and so it precipitates out as a solid, and it's likely to have a colour. It won't have a colour if it's aluminium, but if it's a transition metal, it will have a colour. And of course we get another hydroxonium ion produced as well. So 3 steps, because we have a 3 plus ion. And what I will do quickly is I'll do the overall reaction, because the overall reaction goes from the starting product to the starting reactant to the finishing product. And I'll just summarize that in this little space that we've got here. As we started off with our metal ion with our 6 water ligands, all with a 3 plus charge, and we reacted it with 1, 2, 3 water molecules, and that is in equilibrium with our product, the final product here. So we can draw that out without the square brackets because it has no charge. We've got 3 hydroxide ligands cancelling out the 3 positive charges of the metal ion. We've still got 3 water ligands left, and that's a solid. And we've made 3 hydroxonium ions in the process. So that's our overall reaction for a metal 3 plus ion when we add hydroxide to it. So the key takeaway from it is that we get a precipitate formed, which has a distinctive colour if it's a transition metal, and that distinctive colour of the precipitate will aid identification. But we're going to go into the colours later on. So what we want to do next is we want to do the exact same thing for the metal 2 plus ion. It's very similar, but just it takes 2 steps instead of 3. So what we're going to do is, we're still in our first way of hydrolyzing metal aqua ions, which is adding hydroxide ions, but now we're going to add it to a metal 2 plus ion. So that might be a copper 2 plus ion or a iron 2 plus ion. And because we've only got 2 charges, it only takes 2 steps to create a neutral compound and therefore a solid precipitate. So let's write out our starting reaction, which is our metal 2 plus ion this time. We've still got 6 water ligands, but our 2 plus charge on the complex, we're going to react that with a water molecule, and that's going to be in equilibrium with the first hydrolysis product. So that's our metal 2 plus ion, our hydroxide ligand, because it's one of the water ligands has lost its proton, and we're left with 5 water ligands left, but our charge has dropped down to 1 plus, and we've created this hydroxonium ion like so. But of course we've also added OH minus to it, and so these two react to make 2 water molecules, sucking this out and therefore drawing the equilibrium in this direction, such that this whole thing all happens again, and we get this as our reactant. Writing it out again, we've got our 1 hydroxide ligand, our 5 water ligands, complex with the 1 plus charge, reacts with 1 water molecule in equilibrium with our metal ion and 2 hydroxide ligands, 4 water ligands, but this time we don't write the square bracket, we just write solid in there because it is now neutral, and we've made another hydroxonium ion, don't forget that, and that's our 2 steps to create this solid precipitate. So this is our solid precipitate, and this would have a distinctive colour, one colour if it's a copper 2 plus, and a different colour if it's an iron 2 plus. Now the next point to note is that all these precipitates that we've made, we can redissolve by adding some acid. Right, so if we add some hydrogen ions from the acid, then what happens is that our precipitate acts as a bronzed Lowry base and accepts that proton, and that proton is accepted specifically by one of the hydroxide ligands here, right, and turns itself back into a water ligand. So that would look like this. So you still get your metal, in this case a metal 2 plus ion. You've still got one of the hydroxide ligands left. The other one has reacted with the hydrogen ion to make a water ligand, and so instead of having 4 water ligands, we now have 5 water ligands, and it's got its charge back, and therefore it redissolves. So we'll put a little aqueous in there, so it only precipitates out if it's neutral, and that can happen again. So we can add another hydrogen ion to this, in which case we would get back to where we started from with our metal 2 plus ion, and in this case now the remaining hydroxide ligand has turned back into a water ligand, so we have not 5 but 6 water ligands, and we have a 2 plus charge on our complex, which again is still aqueous. So what we've done is we've redissolved that precipitate by adding acid, and what's happened is that the solid precipitate has acted as a base by accepting that proton, and in the process has been redissolved. And that same process would happen if it was a metal 3 plus ion, except there'd be a further step required to get back to the metal aqua complex. Now that happens, so let me change colour. This process happens, so this process of redissolving the precipitates, where the precipitates act as Bronsted-Lowry bases, happens with all four metal ions. So our copper 2+, our iron 2+, our iron 3+, and our aluminium 3+. This process happens with all of those and gets back to the metal Aqua complex. But what's interesting is that just the aluminium precipitate, the aluminium hydroxide precipitate, just that one can not only act as a base, as all of them do, but also it can act as an acid, in which case if it can act as an acid or a base, the aluminium hydroxide precipitate is called amphoteric. And we'll illustrate that with the reaction on the next slide. So here we are, aluminium hydroxide is amphoteric. Let's show you by means of the reaction. So we've got aluminium. This aluminium hydroxide is Al metal 3+ ion with 3 hydroxide ligands and 3 water ligands, all neutral, right, and as a solid precipitate. And what we're saying is that as well as redissolving in acid, it also redissolves in alkali. So that by acting as a Bronsted-Lowry acid, because it donates a proton, and this is how. So we've added our hydroxide there, and what happens is we've still got our aluminium 3+ ion in the middle of the complex, but we now have 4 hydroxide ions because one of these water ligands has donated a proton and turned itself into a hydroxide ligand instead, and leaves us with only 1 water ligand. But of course that is now charged because it's lost a positive proton, which means the complex is negative and is therefore soluble. And if it's donated a proton, it needs to, that proton is going to latch onto the hydroxide ion that we've added to make a water molecule. This is the hydroxide ion, and the proton latches onto that, makes this water molecule there. So just to repeat, our aluminium hydroxide precipitate not only can accept a proton and redissolve, but it also can donate a proton. It donates a proton from one of the water ligands, and that water ligand would therefore turn into a hydroxide ligand, which has a negative charge. And so the complex now has a negative charge, which means it's soluble. And therefore you can see that aluminium hydroxide is amphoteric. And just for the sake of completeness, I'll say that this doesn't happen with the other 3 metal ions. So if we picked iron 3 hydroxide, for example, so the exact same thing for iron. If we added hydroxide to that, what we don't get is what I'm writing out now. So for iron 3+, iron 2+, and copper 2+, this doesn't happen. So iron 3+, iron 2+, and copper 2+ are not amphoteric, but aluminium hydroxide is amphoteric, and that's quite useful because it can be used to identify that aluminium, if that's what you want to do. If you remember, we were trying to answer this question: what are the different ways of hydrolyzing metal aqua ions? And we've dealt with the first way, which was to add hydroxide ions from a strong alkali like sodium hydroxide. But the second way that we mentioned was we could add ammonia. Because when ammonia dissolves in water, it reacts with the water and you get ammonium. And because it's accepted a proton from a water molecule and leaves that water molecule as a hydroxide ion. And of course, you'll recognize these. These could become the ligands in the metal complex. So in effect, it's the same as adding hydroxide ions, because those hydroxide ions substitute for the water ligands and become the ligands themselves. So let's write out such a reaction, switching colour a little bit, I think. Let's do it for the Fe3 plus ion. So let's have Fe3 plus ion. It starts off with just our 6 water ligands, and we're not going to go through all 3 steps. We're going to add all 3 ammonia molecules straight up. Forgot my square brackets here, just put them in now. And they are in equilibrium with our final product, which has 3 hydroxide ligands instead that have been created from our 3 ammonia molecules turning into 3 ammonium molecules. So 3 of our water ligands have been substituted by hydroxide ligands, leaving only 3. It was a 3 plus ion. We've got 3 hydroxide ligands, so the whole thing is neutral, and therefore we've got no square brackets, and instead we put a solid state symbol there because that precipitates out, and as it happens, that is a brown precipitate. I'll even write that in a brown colour if it helps you remember. But let's not forget our 3 ammonium molecules that we created there. Now this reaction here happens like this for obviously Fe3 plus, because we've just done it up there, but it also happens in the same way for Fe2 plus and aluminium 3 plus, and it happens just like that for copper 2 plus. But if you add excess ammonia in excess ammonia, copper 2 plus metal aqua complexes react further. React one further step. So let's illustrate that one. So we start off with our copper version of this precipitate. So it's a copper 2 plus ion, and we've got, it's a 2 plus ion, so we've got 2 hydroxide ligands and 4 water ligands. And it's a solid because it's neutral, and it's a precipitate, and we can add, if it's excess ammonia, we can add another 4 ammonia molecules to it, and that turns it into a solution that looks like this. We've still got our copper, we've displaced both of those hydroxide ligands and 2 of the water ligands with those 4 ammonia molecules that turn into ligands. So we've got our 4 ammonia ligands and only 2 water ligands. Ammonia is neutral and water is neutral, so our complex has a 2 plus charge on it from the copper 2+ ion, and we have displaced 2 hydroxide ions and also 2 water molecules. And this only happens with copper 2+. This is aqueous, and so what we get is actually a dark blue solution instead of a precipitate of a different colour. Okay, so that's that, because that's unique for copper 2+. That further reaction in excess ammonia can be used to identify copper. And lastly, the third way of hydrolyzing metal aqua ions is by adding sodium carbonate. And the thing about adding sodium carbonate to these complexes is that you get a different reaction, quite a different reaction, depending on whether you use a 2+ ion or a 3+ ion. All right, so for metal 2+ ions we get one reaction, and for metal 3+ ions we get a different reaction. When we react metal 2+ ions with carbonate ions, this is what we get. It's quite a simple reaction. Let's write our complex out. We've got the metal ion, we've got 6 water ligands, and our complex has a 2+ charge. And our simple reaction in this case with the carbonate ion is that we get a simple reaction between the carbonate ion and the metal 2+ ion to form a metal carbonate, which is insoluble, drops out as a precipitate, and our 6 water ligands become 6 water molecules. Like that. So that's quite simple. That's what happens with our 2+ ions. So you're going to get a carbonate precipitate in both cases. Whereas when we use a metal 3+ ion, we get a different reaction. And the reason it's different is due to the higher acidity of the metal 3+ metal aqua complex. Now you remember from GCSE that when you react carbonates with acids, you get carbon dioxide coming off, and a salt produced. So this is how it looks like in a reaction. We've got our metal 3+ ion with 6 water ligands, but this time it's a 3+ charge to our complex, and we're going to react carbonate ions with them. We'll balance it in a minute, but this carbonate ion goes off and reacts with the hydroxonium ion instead, and what we get is the metal hydroxide precipitate instead. So we've got our metal 3+ ion, we've got our 3 hydroxide ligands, and we've got only 3 water ligands left. That is neutral and drops out as a solid as well, but it's a metal hydroxide solid. This has turned into a carbon dioxide molecule and left an oxygen to react elsewhere. So we've got some carbon dioxide coming off, and of course in acid-base reactions we've also got a bit of water coming off as well. And what remains is just to balance it. So we need 2 of these, 3 of these, 2 of these, 3 carbon dioxides and 3 waters. So that's what happens with the metal 3+ ions, and that looks quite different because if you've got a gas coming off here, carbon dioxide is going to be a gas, so in the reaction you're going to see effervescence. you're going to see bubbles of carbon dioxide coming off, which you won't see when you add sodium carbonate to metal 2+ ions. So that's going to allow you to distinguish between the metal 2+ ions and the metal 3+ ions. And that completes this rather marathon lesson, this monster lesson. Well done for persevering all the way to the end. Let's just, as usual, tick off our learning objectives. First one was what happens when metal compounds dissolve in water. Well, we get metal aqua complexes. And we've had plenty of practice of writing those out now. How come metal aqua complexes are acidic? Well, because the metal ions are very positive, 2+ and 3+ in these cases, they draw electrons to themselves, and that weakens the oxygen-hydrogen bond in the water ligands, and so that dissociates that bond in some cases, which expels a hydrogen ion, which makes the solution acidic. And we noted that because of the higher charge density of the metal 3+ ions, so the metal 3+ ions are more acidic because of the higher charge density. That's the second one as well. And the different ways of hydrolyzing metal aqua ions, let's see if we can remember them. As well as just dissolving them in water, we get a bit of hydrolysis, but also we can add hydroxide, we can add ammonia, and we can add sodium carbonate. And our 4 metal ions react slightly different in each case, and that allows us to identify them. And there we have it. Well done.